Okay, so we're going to look at this function right here. We're going to take a look at it on Desmos. So this is it right here. We're going to see what are the zeros, what are the x-intercepts, what are the known factors. So that is negative 2x squared plus 2x, negative 2x to the fourth plus 2x squared. Let's go to Desmos and see what it looks like. So 2x squared. All right, so here we go. This is actually one that's not going to require me to zoom out or change the settings too much. Although I always like mine to be counting by ones. I don't know. I just find that to be a little better. For some reason, it defaults to counting by like 2 on Desmos, which I always find annoying. All right. So again, yeah, I don't really need to change my scaling, and I can see all of my zeros are right here. I have 3 zeros for this 4th degree polynomial. What else are we supposed to answer? Okay, zeros, x-intercepts, known factors. Cool. So going through all those things, my zeros, I have x equals -1, x equals 0, x equals 1. All of these numbers are my zeros. That's the same thing as my x-intercepts, except I guess my x-intercepts are coordinates, they're points. So these are my x-intercepts. And then known factors. So remember, if you have a 0, that also relates to a factor. So if you have a 0 of a, that means that you're going to have a factor of x minus a. So since I have a 0 of -1, that means that I'm going to have a factor of x minus -1. Or we usually just write that as x plus 1. So that's one of my known factors for this x plus 1. If I have a 0 of 0, that means x minus 0, or actually just x, is a known factor. And then if I have a 0 of 1, then x minus 1 is going to be a known factor. So I know 3 of my factors for this. I'm missing 1 of them. So this isn't the full factored form because this would only give me x to the 3rd. So I am missing 1 of the factors. So what I'm actually going to do is think about this totally algebraically. I'm going to kind of ignore the graph for a second, and I'm going to go back here and actually try to factor it. So let me clear what I got going on. So let's go back here and let's take a look at this and factor it. So first thing when you're factoring a polynomial, just in general, you want to check and see if there's a GCF, something you can take away from everything. And I know I can take away, I can factor away the -2, and they both have x squared at least. So I can factor away -2x squared. That's something I can take away. Okay, so then I need to figure out what is left. I like factoring away a negative because that's my leading coefficient is negative, so I'll factor that away and kind of see what's left. I could just factor away 2x squared, but I think it'll be a little easier if I factor away the negative. When I do that, that's going to leave x squared here because x squared times x squared gives me x to the 4th. And if I factor away x squared, that means that's gone together. -2, that's going to leave actually a -1 here, so that when I distribute, if I were to distribute this back in, a negative times a negative would end up giving me that positive there. Okay, so now I've got this. I factored away my GCF. Now the only thing left is to see if this factors any further, and this, hopefully we notice, is difference of squares. So difference of squares, this is really x squared minus 1 squared. So this is going to factor as x plus 1 times x minus 1. And so those were two of the factors we knew from graphing it. We did already know that these were going to be factors when we looked at the graph. And we knew an x was going to be a factor, but there was actually x was a factor twice. So this would be our fully factored form of this function. We figured out all 4 factors because we had this one here was actually a factor twice. There are some keys to the graph that actually would have given us some information about that. So the way that a graph behaves at your x-intercepts will actually give you some information about whether a factor is actually repeated, like in this case where our factor was repeated multiple times. All right, let's go ahead, clear that. So we factored it like this. This particular factor, which I was saying before, was repeated twice. And if I look at which 0 that was associated with, take a look at what's happening right here. This was the factor that was, this was the root or the 0 that was associated with this particular factor. Notice how this x-intercept, this 0, was a little bit different than these other ones. Right here, the graph passes straight through the x-intercept, just goes through it, turns, whatever. But on this one, it does this thing that I'm going to call a bounce. Whenever it does this bounce, that means that the factor that's associated with this is repeated, meaning that it's actually it's repeated twice. There are some other ways that they can go through. If we have a 0 here, you can also get something that goes like this, where it doesn't quite go straight through. It does this kind of wiggle. These are not technical terms, but I like to describe them this way, where it bounces off the x-intercept or it kind of wiggles through the x-intercept. Both of these two things will tell us that whatever factor we're looking at is going to repeat. Whenever we have a repeating factor like this one, I wish that would just go away. Whenever we have a factor that's repeating or a 0 that's repeating, we need to be able to determine how many times it repeats. We call that the multiplicity. So if you solve a quadratic equation and you get some particular 0 more than once, so you factor it and you end up with like x minus 1 times x minus 1 times x plus 3, and this is the factored form. These two things are both going to give you the same 0. This factor and this factor will give you a 0 of 1, whereas this one will give you a 0 of -3. This factor has what's called multiplicity, and that causes some interesting behavior, all kinds of different things. So if we have an even multiplicity, so this one has a multiplicity of 2, that thing that we just saw in the previous graph happens. I call it a bounce. Instead of crossing the axis, whatever the 0 is, it's going to go into it and it's going to bounce off of it. So if this was our x-intercept, instead of going through it there, it's going to touch it and bounce, but it won't cross. It could come from the other direction too. It could come from the bottom and bounce this way, depending on the graph. So whenever we have an even multiplicity, it's going to do this thing. It's going to bounce. If the multiplicity is odd, then it's going to do what I'm going to call a wiggle. Again, not a technical math term, but I think it makes sense. So what that looks like is if you have your x-axis and you have a multiplicity that's odd, so like maybe we had another factor of x minus 1. So this one has a multiplicity of 3 now. It's going to do this. It's going to go towards it, and it's gonna kind of do this wiggle thing and then curve. So instead of just going straight through it, I don't have a better description for it. I like the term wiggles as it's passing through the x-intercept. So we can use the graph to kind of help us decide if any of our factors or any of our roots have a multiplicity. That's actually going to be really useful because we can kind of use this, the way that they cross through the x-axis, to give us an idea of whether any of our factors are repeating, because that can be one of the hardest parts about this is figuring out all the factors. And if we can figure out that a single factor repeats multiple times, that can help factor higher degree polynomials much easier. So we're looking for bounces and wiggles. Sounds like a kid's show. Wiggles. Wiggles is a kid's show, right? Or they like make music or something. So again, just to sort of repeat that, for a normal x-intercept, it just kind of crosses through, passes kind of straight through it. If it's an even multiplicity, it does this thing, it bounces. And for an odd multiplicity, it's not going straight through, it wiggles. So we're going to be looking at some graphs and trying to decide if we have a normal x-intercept, an x-intercept with an even multiplicity, or an x-intercept with an odd multiplicity. So we can really use Desmos to our best advantage here by kind of graphing them and really analyzing these x-intercepts this way. So let's check this. Let's look at this. What are the zeros? Well, the zeros are all associated with our factors, right? So this one would just say 0 is one of our zeros. This one here, which repeats, it has a multiplicity of 3. Multiplicity. Also this here, multiplicity of 2. This one would give us a 0 of 1, right? 1 minus 1 is 0. And this would be a 0 of -2. So -2 would be a 0 for this one. So these are the 3 zeros. This one is just a normal 0. It's going to pass straight through there. It only happens once. So this one is a normal, gives us a normal one. This one has an odd multiplicity, so it's going to do that wiggle through there. And this one has an even multiplicity, so it's going to be bouncing at that number. So when we look at the graph, that's what we're looking for. So this one has a multiplicity of 1, only shows up once. This one has a multiplicity of 3, remember odd, and -2 is going to be a multiplicity of 2, that's even. So when we look at the graphs, we should be seeing some bounce at -2, a wiggle at 1, passing straight through at 0. And this would be a 1, 2, 3, 4, 5, 6th degree polynomial. Is everyone kind of catching on how I counted that? I have x, then I have x to the 3rd, so x, then 1, 2, 3 more is 4, and then 2 more is 6. So I'd end up with x to the 6th if I multiply this all out. I'm going to clear this and look at the Desmos graph for this. -x minus 1 3rd x plus 2 squared. Okay, I actually don't really need to zoom this one out too much because all I'm really looking at are the x-intercepts here. I actually may even want to zoom in on them a little bit. So we can see, okay, x equals 0. That root had a multiplicity of 1. So you can see how it just passes straight through there. This one, -2, has a multiplicity of 2. So you can see how it's bouncing there. So the graph is kind of, if I just was looking at the graph, I could already know that this has a multiplicity of 2 probably. And then here at 1, you can see that wiggle where it's kind of changes directions while it's going through there. It kind of swerves, goes through, swerves again. That's what we call that wiggle. So that one again is telling me I do have that odd multiplicity going on. So we can really use Desmos as a tool for factoring. That's what I'm really getting at. Using the graphing programs to help us figure out what the zeros are and therefore how to factor these higher order polynomials, because it can be really hard. It can turn into sort of a guess and check game when we deal with really high degree polynomials, and that's not fun or useful. We would like to be able to figure out what the factors are quickly, or what the factors might be quickly. And especially if we can figure out factors that have a multiplicity, we kind of figure out multiple factors at once, which is super nice. So this is why I'm kind of showing this and talking about the behavior of the graphs at these places. All right, going back. All right. Example 2, multiplicity. Do any of the zeros of this function appear to have multiplicity? All right, well, looking at it, the zeros, right? We have a 0 at 0, and we have a 0 at 1.3 repeating. So we have 2 zeros. Do either of these look like they have multiplicity?
Only one.
Yeah, this one here, is this an odd multiplicity or an even multiplicity?
Odd.
Yep, so it's doing that wiggle thing, right? It's kind of curving twice as it goes through. So this one looks like it has an odd multiplicity. And hopefully we could actually sort of see that, because if I go to factor this, first thing I notice is I can factor out an x cubed. So that leaves us with 3x minus 4. This one's not too hard to factor. I can see this right here has a multiplicity of 3. And that would give us this 0 here. If I set that up, right? X cubed equals 0. X equals 0 is going to have a multiplicity of 3. And this one would only have a multiplicity of 1, which would give us, I guess, would give us this 0. Add 4 to both sides. Divide by 3. 4 over 3 is, okay, yeah, 4 over 3 is 1.3 repeating. So we can see our two zeros pretty easily by factoring, because this one wasn't too complicated. But yeah, this one does have an odd multiplicity, and actually specifically a multiplicity of 3. So kind of checking out the graph gives us some idea of what kind of factoring we might end up looking to do. Anytime 0 is a 0 of your function, you know that you can factor out an x, at least one x. So, because that's how we end up getting x equals 0 as a 0. X equals 0 as a 0, that's almost a tongue twister. All right. Whew, there's a lot to this. I don't know how I thought we were going to get through 2 sections this week. I feel like a crazy person as I go through it. All right, multiplicity example. Here's a pretty crazy looking polynomial. There's a lot of turns and wiggles and bounces and all kinds of things going on. We're looking at our zeros. There are 3 of them. There's this one right here, this one right here, and this one right here. Just looking at them, I can see 3 different things. This one looks to have an odd multiplicity because we're getting that wiggle. This one looks to be a normal x-intercept. It's kind of passing straight through there. It's not wiggling or bouncing or anything. And this one looks to be an even multiplicity because it bounced. It goes down, touches it, bounces up, didn't actually pass through. So just knowing that, I could give us a pretty good idea of what the factored form would be, right? -5 would give us a factor of x plus 5. Odd multiplicity means it's probably to the 3rd power. It could be a higher odd number, but 3 is a good start. Normal means that it just shows up once, so this would be x plus 1. And even means it could be 2 or 4. I'm just going to guess 2. So we have x minus 1 shows up twice. I have a pretty good idea of what this equation is already, at least its factored form. I have a pretty good idea that this equation is x plus 5 to the third power, x plus 1, x minus 1 squared. Now, you can see it, right? That's the equation. This is the equation for this particular graph. Now, there could be a multiplier out here in front. You know, we could have a multiplier of 3 that we're not accounting for. Or we could even have higher degrees on this. This could be like to the 4th power or 6th power. But if I knew my original equation and I was just looking for this factored form, I could get a really good idea of how close this was to the actual factored form. And we'll get into that next section when we try to decide how to fully factor these more complicated polynomials. I mean, this one right here is 1, 2, 3, 4, 5, 6. This right here is a 6th-degree polynomial. That's about as complicated as we would ever get, to be honest. We probably won't go any more complicated than that because that's pretty high. Is everyone understanding how I identify these different things? The bounce, the wiggle, the even degree, the even multiplicity, the odd multiplicity. Yeah, a lot going on here. Okay. Let's go ahead and clear this. We have 8 minutes. It's decent. Okay, so again, I've been doing this a lot, but we need to know that if you have the zeros of a polynomial, if you know what the zeros are, then you can write the factored form. So this is how we can use Desmos graphing to help us factor. We can graph it on Desmos. We can see what's going on with it. We can figure out these zeros, right? And wherever those zeros are, those are going to tell us some factors. So that's actually really useful. Instead of going through all the different ways we learned how to factor, we can kind of look at the graph and see what the factors are going to have to be. So it's a nice tool that we have at our disposal. These are all x minus, but remember also that if you have something like, let's say this number here represented a negative number, which is what it looks like. Say this was -5, remember the factor would actually be x plus 5 because minus and negative is the same thing as plus. So they're not all going to be minus. Some of them are going to be plus if our zeros were negative numbers. All right, so let's go ahead and write a polynomial function with these zeros. I'll pause for a second. See if you can write the factors that go with these. Function, I guess, so f of x. Write out your factors. So -3 gives us a factor of x plus 3. 0 gives us a factor of just x. Usually if we have a factor of just x, we write that one first. So I'm just going to mess with the order and put that one first. 2 means that one of our factors is going to be x minus 2. And 4, with a multiplicity of 2, means we're going to have x minus 4 twice. So power of 2. So there we go. This is a function that would have these zeros. Proper multiplicity on that one. Not too difficult. And a lot of times, just looking at the graph on Desmos, we can see these points, right? We can see, okay, there's that point, yeah. We can see these points, so we can write out the factored form of a polynomial. It gets complicated if some of our points are decimals and things like that, but more or less it's going to hold. That we'll be able to kind of look at the graph and figure out many of the factors. All right. Let's go to old-fashioned factoring, though. So this is going to happen a lot. All your terms have an x in them. Cubics are ones that I really think you can do by factoring the whole thing rather than using the graph, but you could look at the graph too. So if all your terms have an x, make sure to factor that out. And then factor that remaining quadratic. We should be able to factor quadratics pretty easily. We're looking for two numbers that multiply to -2, add to -1. That's going to be -2 times +1. So this factors as x minus 2, x plus 1. So there we go. This is fully factored. This is going to give us x equals 0 as one of our zeros. This one would give us x equals 2 as one of our zeros. And this one would give us x equals -1 as one of our zeros. It's a pretty easy process, especially when we're dealing with something like this, where this is just a degree 3 polynomial. Degree 3, most of the time, they'll be set up in such a way that you can probably just factor them, you know, without too much extra fancy steps going on. But we could check out Desmos and come up with these same answers that way too. All right. So this is another cubic. What is the end behavior? Ooh, end behavior. We haven't really talked about that in this section or this today. So this is an odd degree. And we have a negative leading coefficient. So if we check our end behavior chart, that means that it's going to be up on the left side, down on the right side. Odd means they go in different directions. And negative means it's going to have a general decreasing trend, meaning it'll be high on the left and low on the right. So up on the left, down on the right. If it was a positive leading coefficient, it would have a general upward trend, so low on the left, down, up on the right. So that's going to be our end behavior. Find the zeros by factoring. So just like the last one, all these terms have an x in them. So I can factor that out. And generally, when you're factoring, you don't like the leading term to be negative. So you want to factor out a negative also. So I'm factoring out negative x. So that's going to leave 4x squared minus 12x plus 9. Because when I redistribute that negative, that would be negative 4x plus 12 minus 9. Yeah, okay. Whenever you factor out a negative, you essentially just change the signs of each term, right? Okay, well, one of my zeros is easy. X equals 0. These ones are going to be a little harder because factoring this one's going to be a bit more difficult, especially because of the leading coefficient of 4. I'm using this type of factoring. You could do it however you want. 4 times 9 is 36, negative 12. So I need two numbers that multiply to 36 and add to negative 12. 18 and 2, 9 and 4, 12 and 3. Uh, 6 and 6, so minus 6, minus 6. Two negatives multiply to be a positive. These would add to be negative 12. And then we want to simplify both of those, so that's 2x minus 3 is one of my factors. Well, it's the same on both sides, so this one ends up being 2x minus 3 also. So this actually has a multiplicity of, so one of our zeros is going to have a multiplicity of 2. And when we figure out that 0, we end up with x equals 3 over 2. It is 43. I'm going to finish this problem, but if you got to go, let me know, or you can just go. 3 over 2 is 1.5, so that's right there. Since it has a multiplicity of 2, it's going to bounce there. So on the left side, our graph is going up. We're going to have to curve back here, and we're going to have to bounce and go back down. So our graph should look something like this. I use the in behavior to know it needs to go up on the left, down on the right, and I had to kind of fill in the curves to make it do what I wanted. And I knew that this was going to be a bounce because of the multiplicity, because this root happened twice. Do the 2.2 homework, send me emails if you